Hello everyone, welcome to our problem 1 of slope deflection method. In this method, we are going to solve this example, solve this problem number 1. This is going to be our problem number 1. We are going to solve this two-span continuous beam by slope deflection method, and then we are going to draw the bending moment and shear force diagram. So firstly, fully we have learned the basics of slope deflection method. So if you don't know the basics of slope deflection method, if you don't know about the fixed end moments, and if you don't know the slope deflection equation, you need to know these two points: fixed end moments and slope deflection equation. I've already created a previous video about that. You can check that out through my playlist of structure 2. So let's move on to our problem. So what we're going to do is we have a beam over here. So let me draw the beam. So we're going to solve this by slope deflection method. So we have fixed support at A, we have a roller support at B, and similarly we have a fixed support at C. Then we have a 20 kilonewton for we have a UDL over here. Next we have a point load of 40 kilonewton, which is acting at a distance of 2 meter and 2 meter, okay, like this. And this is my point B, and this is acting over a span of 6 meters. So I have I and 2I as well. So firstly, what I need to do is first step 1. So whenever you are solving by slope deflection method, firstly you need to calculate the fixed end moments. So there are different case scenarios to calculate fixed end moments, and there are different formulas involved. So let me show you over here fixed end moments. So we have different case scenarios where the point load is acting at equidistance, and if it's acting at a different distance, if we have UDL, if we have UDL acting over the span, if we have UBL, which I've already explained in my previous video. So you can take a screenshot of this as well. So right now we are dealing with this case scenario where our point load is acting at equidistance from both the ends. So firstly what we need to do is we need to calculate our fixed end moments MFAB. So what we will do is we'll simply divide this beam in this way. This is my section A, this is my section B, and 40 kilonewton is this way. So my will have WL by 8, and fixed end moment will be this is W this is WL by 8. So this is the formulas for our this case scenario. So this is acting at L by 2 and L by 2. For this case scenario, what you simply do is this roller support will change into fixed support in order to calculate our fixed end moments. So our formula will be minus WL by 8, minus WL by 8. So this is this case scenario. We have WL by 8, WL by 8. For UDL is WL square by 12, WL square by 12. So why the minus sign? Because it's acting in anti-clockwise direction. So anti-clockwise movements are taken as negative. So minus W is minus 40 into L. L is 2 divided by 8. So we get this as minus 20 kilonewton meter. Similarly, fixed end moment BA will be plus WL by 8. So all the parameters are same. So we get this value as. So why the plus sign? Because this is acting in clockwise direction. So we have done for section AB. Next we'll be looking for our section BC. So again, what I've explained before, the roller support will be changed into fixed, and will be changed into fixed end. So right now we are looking at this much of section only. So let me draw this section over here. The roller support changes into this type, and we have uniformly distributed load acting over here, 20 kilonewton. So for this case scenario, the formula is will be looking at this case scenario where UDL is acting uniformly over the whole span. So we get the formula as minus WL square by 12 and WL square by 12. Why the negative sign? Again, clockwise and anti-clockwise, MFBC and MFCB. The formula will be minus WL square by 12 and plus WL square by 12. So on solving this, we will get minus W is 20, its 18 span of L is 6, L is 6 square divided by 12. On solving this, we are going to get a value as minus 60 kilonewton per meter, and this is going to be plus 60 kilonewton per meter. So my step 1 is completed up to here. So my step 1 is completed. So what we're going to do next is we are going to move on to our slope deflection equation. So this is going to be my step 2. What I'm going to do in my step 2 is I'm going to write down my slope deflection equation. So slope deflection equation will be for MFAB, sorry, it will be MAB, MBA, MBC, and MCB. So slope deflection equation is will be looking at each member. It will be looking at each joint. Let's say firstly I'm looking at joint A, I look for member AB, and from joint B I look for BA, from B I look for BC, and from C I look for CB. So this is going to be my slope. Step 2 is calculate or write down your slope deflection equation. Since we are solving by slope deflection method, we need to write down our slope deflection equations. So firstly, this is my formula, MAB equal to MFAB. So firstly write down, right now I'm looking for my member AB. So firstly I'll write down the fixed end moments. Fixed end moment MF AB plus 2EI by L plus 2 theta A. 2 will, the numerical, the constant 2 will be, if I am looking for AB, it will be 2 theta A, but if I am looking for BA, it will be 2 theta B. So 2 will be the slope, the angle. So theta A simply refers to, if the beam deflects in this way, let's say like this way, this will be the angle formed. Theta A simply refers to that angle. So we don't need to go much deeper into that. We can simply remember this as formula 2 theta A plus 2 theta B minus 3 delta by 3 delta by L, where theta refers to the rotation, whereas the delta refers to as deflection, or we can say this as settlement. I've already explained about the brief explanation regarding this in my previous videos. We can see that, but you don't need to go much deeper into this. Just remember this as a formula, and in order to make the remembering easy, what you can simply do is, if I'm looking for member AB, it will be 2 theta A, but if I'm looking for member B, it will be 2 theta B. Otherwise all it will be same. So for MB also there is the formula is exactly the same. Instead of MF AB, I have MF BA 2 theta 2 EI by L theta A. Since I'm looking for member BA, it will be theta A plus 2 theta B minus 3 delta by L. So you can just simply remember this formula. So after doing this, what we're going to do is we are going to write down this formula. So I'm looking for MAB should be fixed end moment AB, which I've already calculated before, plus 2 EI by L. So 2 theta A, since I'm looking for member AB, minus 3 delta by L. So right now the settlement is 0 because no settlement has been given in the question. So we're going to take the settlement as 0. So this so simply this becomes as 0. The settlement will be caused in this way, since there is a fixed end at A, there will be no any rotations. There will be no rotations, so settlement will be in such a way. Such a way, due to this point load, there will be a formation of angle theta B over here, but no any rotations will be caused at a section at end A due to fixed end. Since there is fixed end, or sorry, since there is fixed support, but since there is a roller support at B, roller support, so for fixed end moments we assume the joint B as a fixed end, but while calculating the slope deflections, while right now slope deflections, we are not going to assume it again as fixed end. So there will be a rotation caused at B, it will be usually by theta B. But since there won't be any rotation, so we are going to write theta A as 0 as well. So we have found the formula of we have calculated MFAB, fixed end moment AB, as minus 20. So put minus 20 over here. So put minus 20 over here. 2 EI by L. L is 2 plus 2 is 4. 4. This becomes 0. This settlement also becomes 0. Plus theta B. So on solving this, we are going to get MAB equals to 0.5 EI theta B minus 20. So to remember the value of we have I over here. It is I, while it is 2I for member BC. So while again we calculate M BA. We calculate the MBA for member BA. So in order to calculate BA, let me write down the formula for over here. MBA will be fixed end moment BA plus 2EI by L. Right now it will be 2 theta A, it will be theta A because I'm looking for member BA, but it will be 2 theta B minus 3 delta by, and again the settlement is 0, and again the theta A is 0 because we are right now looking for the same member. We are looking for the same case scenario, this case scenario, and we'll write down the value of 2 theta B as 2 theta B, and on solving this we get MBA equals to EI theta B plus 20. So I'm going to write my L as again 4 I will be I, but let's now look out for member BC. By looking for member BC, the deflections will be caused in this manner. For since there is a fixed end, fixed support, there won't be any deflections. There won't be any rotations, and the rotation will be caused in this way. There will be theta b, but there will be certain value of theta b, but there won't be any value of theta c. It will be theta c will be 0, and again deflection will be 0. Again, we write down the same formula for BC. So it's really easy to remember. For BC, it will be BC MF BC plus 2 EI by L. Instead of theta A, we'll be writing firstly theta B, then theta C. Again, the delta will be 0, but this time theta B won't be theta C will be 0. Theta B won't be 0, so we'll have certain value of theta B. Again, we just simply write down for this. We have to let the value of MFBC as minus 60. We put it down that instead of I, will be putting 2I this time, because for member BC we have 2I given in the question. On solving this, we'll get the formula. We'll get the equation for BC. Minus 60 over here. Minus 60. 4EI divided by L is 6. L is 6 meter over here. This is really simple. 2 theta B plus, so you can just simply write it down. It's not much difficult. Again, we'll calculate MCB as well. MFCB plus 2 EI by L. 2 theta C to theta B minus 3 delta by L. Delta will be 0. Theta C will be 0. We put down the value of theta B. So now we have CB as well. Next, what we'll be doing is, now we'll move on to our step 3. We have completed our step 2 as well. Now what we'll be doing is, we'll move on to our step 3. So what will be our step 3 is, as I explained in my previous video on introduction to slope deflection. Next we'll be using joint equilibrium equation. So what does our joint equilibrium say is, moment at joint is always 0. So at joint B, so we have at joint B we have two moments, MBA plus MBC. MBA going in this direction, and MBC they going in this direction. So so the total moment at B needs to be remained needs to be always 0. So MBA plus MBC equals to 0. So we'll be using that MBA plus MBC equals to 0. Similarly, will be MBA plus MBC equals to 0. So what we do is, we have only one joint over here, that is joint B. So we can use only one joint equilibrium equation. But if let's say we had multiple members, will be using multiple joint equilibrium equation, which we'll be discussing in our other videos. So MBA plus MBC equals to 0. We have calculated the value of MBA over here. MBA is EI theta B plus 20. So put down that, and we have MBC as well. 4 by 3 EI theta B minus 60 equals to 0. So on solving this, we're going to get our value of EI theta B as 17.143. What we can do is, we can simply substitute the value of EI theta B in all the equation 4, equation 3, equation 2, and equation 1, and then we'll get all our required values of MAB, MBA, MBC, and MCB. So we have our value of MAB, MBA, MBC, and MCB. So what I'm going to do is, let me draw the original equation over here. Okay, so this is my so what we can do over here is, let me draw down the original question. So my original question was something like this. We had a roller support at the here, we had a UDL, and we had a point load 2 meter, 2 meter, this is 6 meter, B, A, C. So we had the values as 20 and 40. Okay, we had 40 kilonewton over here and 20 kilonewton over here. So what we have next, what we'll be doing is, we will okay, so this is my, So this is my original question. So what we will be doing is, after we have calculated all our moments, let me paste the question over here. Okay, so this is my original question. Okay, so what we're going to do is we are going to divide the sections. Now we have, let me write down the values of MAB, MBA and MCB as well. So my value of MAB is minus 11.428 kilonewton meter. Similarly, my value of MBA. So you don't need to calculate your individual values in your exam. So let's, if I have calculated my value of MBA as 37.143, I'll automatically know my value of MBC. Because it is going to be MBA plus MBC equals to, which is going to be exactly the negative minus 27.143 kilonewton meter, and MCB is going to be 71.429 kilonewton meter. What we're going to do now is we're going to treat each beam separately with load on it and end moments. What we're going to do is we're going to remove all the supports. We're going to remove the fixed supports, the fixed supports and the roller supports. So let me look for my section AB. So first I look for my section AB. I have 40 kilonewton acting over here, and we'll have RA acting vertically over reaction at A, and I will have RB1. Again, I will draw my section B. Okay, now I'll have RB2 over here. So reaction at B will be the summation of, RB1 and RB2. Next I have UDL acting over here. This is going to be, I'm going to have RC as well. It's going to be my section AB, and this is going to be my section BC. So what I'm going to do is I'm going to write down my moments. So MAB is minus 11.48. Negative means anti-clockwise moment. So I'm going to write it, so it in this way, 11.428 kilonewton meter, and MBA is 37, which is going to be clockwise. So I'm going to write down as 37.143, and MBC is again negative 37, anti-clockwise moment, 37.143, and CB clockwise, which means 71.49. So what we're going to do is we're going to write down in this way. Next we're going to calculate RA, RB1, RB2 and RBC. So what we can simply do is, in order to calculate your RA, what we're going to do is we have can simply use moment. You can take moment at about A as 0. So let me write down a simple equation. What we're going to do is, so right now we can, let's find out RA first. What I'm going to do is I'm going to take clockwise moment at B equals to 0. So RA is acting at a distance of 4 meter. So it's going to produce clockwise moment. Clockwise RA is acting upwards, so it's going to produce clockwise moment. So RA into 4. So 11.428 is negative anti-clockwise moment, minus 11.428. At section B, I have another moment of plus 37.143. So fully we have understood over here. It's just really simple. A simple calculation of reactions and supports. Next what we're going to do is 40. So what is 40 producing? 40 is also producing anti-clockwise moment. Minus 40 into 2 equals to 0. So this is my total moment acting at B. Why negative? Because 40 is acting downward, and it's going to push my beam in this manner. It's going to rotate my beam anti-clockwise to anti-clockwise. So from this I'm going to get my value of RA as let's take all those variables at the right, minus all these values, plus 11.428 divided by 4. So on doing this we are going to get a value of RA as 13.57 13.571 kilonewton. So in order to find RB1, what you can do is you can take again clockwise moment at A equals to 0, but it's going to be a little bit a lengthy process. What you can simply do is you can take all the forces acting downward, summation Fy equals to 0. Since I've already calculated my RA1 is acting upward, so minus 13.57 plus 40 plus RB1 equals to 0. So RB1 equals to RB1. Okay, so this is going to, sorry, this is going to be minus, okay, plus 40. Okay, sorry, plus 40 plus this is going to be negative since I have assumed RB1 to be acting upward, so we're going to minus RB1, so I get my value of RB1 as 40 minus 13.57, which is going to be equal to 26 point something, 26.429. Okay, so let's check this value, kilonewton. Similarly, you can calculate your value for RB2 and RC as well. So take moment at C equals to 0. So this is going to be really simple process. You can have a little bit confusion regarding the UDL. So hopefully you know how you can convert UDL into point load. So let me explain that. So okay, this is my UDL. So this is W per meter, and this is acting, let's say, over of distance L. So in order to convert it into point load, we just simply multiply this value W with the span, and it will act as a distance from L by 2. In this way you can convert this simply into point load, and the moment, let's say if I'm taking the moment about C, this will be WL into L by 2, but there will be negative sign. It's just going to produce anti-clockwise moment, and anti-clockwise moment are taken as negative. So hopefully you have understood how to convert this little bit confusing part. So this is going to be 20 into 6 square, so this is going to be minus WL square by 2. This is just really simple. Hopefully you have understood that. This is just really the same process. This is the simple structure analysis. So after that, what we're going to do is we're going to write down all those values. So RB, so the value of RB will be summation of RB1. So you need to remember this. You have got the value of RA as well. You have got the value of RC as well. So we have our value of RA as 13.571, RB is 86.71, RC will be 65. So what you need to do is next, you need to draw your surface diagram. So right now I'm going to explain briefly how you can draw your surface diagram. So let's look at point A first of all. So at point A we have 13.571 upward, so it will go upward, and this will continue constantly until 40 kilonewton will act downward. So we'll have our surface negative, it will go downward. So it will be 13.571 minus 40, it will be 26.429 kilonewton. Again it will go constantly until it is pushed up by RB, so it will be minus 26.429 plus 86.715, and we get this value as 54.286 kilonewton. Again we will go upward, and it will this value will get a 0 somewhere due to the presence of UDL in this way, and this value will be 65.714, and ultimately surface will be 0. The surface diagram always needs to end at 0. So okay, what you can do is you can simply calculate this point where the surface will be 0 by using similar triangle method. You can use this triangle and this triangle, and you can use the similar triangle rule. Okay, so we have this as, if we take this as x, this will be L minus x. You have this value over here, we have this value as well. So you can simply use a similar triangle rule in order to find this value, or you can use your hit and trial method as well. So why we need this point is because at this point my bending moment will be maximum. So in order to find the bending moment, firstly the negative is taken upward. In order to calculate BMD, you need to understand that. So I have done this in my previous. So if you are a little bit confused regarding how to calculate this shear force diagram, so let me just write it over here. What we're going to do is we are going to use a similar triangle method. So this is going to be x, this is going to be L minus x, where our L is going to be length of BC. So length of BC is 6, I think. 6 minus x, 6 minus x, and we're going to have this value as 54.286, and this is going to be 65.714. So what you can do is you can simply write down 54. Okay, 286 divided by x equals to 6 minus x divided by 65. I think this is the formula. Sorry, I just wrote it opposite. 65.714 divided by 6 minus x. So using your similar triangle method rule, you can just find out your value of x. So we have 11.478. The negative is we're going to write a negative upward because it is opposite for your bending moment diagram. So we have this moment 11.478 over here, and this is going to decrease to something over here positive value. Again, it will increase up to here 37.143. This is going to be, we have already calculated this value over here, 37.143, and it will end with 71.429, 71.429 over here. And we need to find our bending moment at this point and this point as well. So this is just really easy. In order to find your bending moment diagram, we have our distance from point A. So how we have calculated a moment over here, moment at B equals 0, you can simply calculate a moment at point D, which is distance of 2 meters from it. It's just really simple. You can see my previous video as well, regarding constant deformation, where I've explained easily. So hopefully you have understood how you can solve a beam by slope deflection method. So if you have any queries, you can comment down below, or you can reach me through my Facebook or Instagram page as well. So in our next video, we'll be solving this example 2. Example 2 will be finding out the support reactions and drawing the bending moment and surface diagram for this beam, where we have a certain deflection. The support B sinks by 30 m. It's going to be a little bit different than problem 1. So if you have any queries, please do contact me, and if you like our content, do subscribe the channel, do like the video, and do share with your friends. Your support means a lot. Thank you.